Hi guys, if I bang my arm on the desk, is there a probability that my arm could reach the other end of the desk? Of course guys, there's a non-zero probability that my arm could reach the other end of the desk. If you are a Harry Potter fan, in the Harry Potter movie series, to get to platform 9 3/4 at London's King's Cross station, you need to go through a wall. All this is explained in quantum mechanics. Classically, for objects as large as your arm cannot reach the other end of the desk. But in quantum mechanics, there is always a non-zero probability that your arm could tunnel through to reach the other end of the desk. When you get to smaller and smaller objects and reach particles like fundamental particles, and let's get an electron for this instance, there's always a probability to tunnel through. In nature, tunneling takes place all the time. Without quantum tunneling, the sun would not shine. It plays a major role in the fast computers that we use at present. This is because of the transistors inside them. 13.8 billion years ago, the universe was created due to the Big Bang. Quantum tunneling may have influenced this phenomenon. So guys, what's quantum tunneling? Is it magic? The answer is coming up right now. Hey guys, here I have a tennis ball in my hand, and we consider these two barriers to act as a particle inside a box model. So this very tennis ball could move back and forth in this particular region, and we consider the region that it travels as the x direction. Also, we consider that this particular surface is frictionless. So there is no influence on that particular tennis ball and is also called a free particle because there is no external influence on the tennis ball. If I ask you a simple question, how can a tennis ball reach the other end of the barrier? Either you need to have sufficient energy in the ball to go over the barrier, or you need to go through the barrier and reach the other end of the barrier. However, classically, you can move the ball over the barrier if you have necessary energy, but there is no probability that you could break through the wall and have the ball on the other end of the barrier. In the quantum world, however, this is possible. If we consider this ball to be an electron or a fundamental particle which is very small, there is a probability that this particular electron could tunnel through the barrier and reach the other end of the barrier. So why does this happen? This is because the electron has wave-particle duality, and the electron particle behaves as a probability wave. The wave function related to the electron would tell us the probability of finding the particle at a particular location. This phenomenon shows that the wave function behaves till infinity, or it behaves in all space. All of this is explained by the Heisenberg's uncertainty principle. We can find this by the Heisenberg's uncertainty principle. In the year 1927, German physicist Werner Heisenberg developed the Heisenberg's uncertainty principle. Delta x, which is uncertainty of position, times delta p, uncertainty of momentum, is always greater than or equal to h hat over 2, where h hat is h over 2 phi, and h is the Planck's constant. Practically, we cannot find the 100% exact position of the electron. If we know the position of the electron, the momentum of the electron is not known. Conversely, if we know the momentum of the electron, the position of the electron is unknown. And this is always greater than or equal to h hat over 2. This is the Heisenberg's uncertainty principle. There is a wave function for the electron. Usually this is sinusoidal. The probability of finding the electron is governed by the Schrodinger's equation. Here we have the time-independent Schrodinger's equation. We have already discussed about the Schrodinger's equation in our previous videos. The link to the playlist is given in the description. The Schrodinger's equation was developed in 1926 by Austrian physicist Erwin Schrodinger. Here we have the time-independent Schrodinger's equation, where we don't have the time term or the t term. Here, the psi x term in the Schrodinger's equation is the wave function. The square of the wave function is the probability of finding the particle in that position. Psi x can be positive or negative, but the psi squared x term is always a positive. So guys, simply this is the time-independent Schrodinger's equation which created a revolution in the field of quantum mechanics in the 20th century. Let's consider the following graph as an interpretation for the particle inside the box model. It has a finite distance, a finite height, and also a finite thickness. There are 3 regions in it. Here we consider the total energy E is less than the potential energy V naught. The region 1 is a cosine function, the region 2 has an exponential decay, and the region 3 is also an cosine function. When we apply the Schrodinger's equation to the region 1, we can see that the potential energy term is 0. So the entire term of Vx times psi x cancels off. So after we simplify the equations down, we can obtain the wave number k1 squared as 2me over h hat squared, which is simplified as k1 is equal to square root of 2me over h hat squared. And the wave function psi1x is equal to a times cos k1x, and here it's a cosine function. And the term a here is the amplitude of the wave function, and the cos k1x is the cosine function. In the region 2, there is always a potential energy V naught in the barrier. So when we simplify down that term, we can see that the wave number here is equal to 2me times V naught minus E over h hat squared. And we can also obtain the k2 dash term squared, which is also equal to 2me times E minus V naught over h hat squared. Here the wave function we have is psi2x is equal to c times e to the power minus k2x, which is an exponential decay. The exponential decay term comes with this e to the power minus k2x, and the term c here is the amplitude of the wave function we have, and it comes to the region 3, and the wave function psi3x is equal to d times cos k3x. Here it's a cosine function. You can see that the probability is directly proportional to the amplitude, and the amplitude is directly proportional to the probability vice versa. So when the probability is high, we can see that the amplitude is also high. If the probability is less, the amplitude will also be less in our wave function. So the factors that determine the tunneling effect are mass of the object, simple m, height of the barrier, which is V naught. Now V naught is the potential energy of the barrier. The thickness of the barrier is in simple x. These are the factors related to tunneling effect. Where do we see tunneling in the real world? The electron devices that we use are mainly made of transistors. There are different types of transistors. However, all the transistors function in the same way. There is a source, a drain, and a gate. The gate controls the electron flow inside the transistor. If the gate is too small, the electrons will tunnel through the transistor and destroy our circuit. This is why in the modern day we can't make transistors any smaller. Stars shine due to fusion. When you take the hydrogen atom for an example, it gives out helium atoms and energy in the form of radiation. Hydrogen bombs also work in a similar manner. Tunneling plays a vital role in the fusion process of the Sun. As hydrogen has protons in it, it is positively charged. So to overcome the barrier or the Coulomb potential, it needs an extremely high energy. But the tunneling phenomenon is seen here. So it doesn't need enough energy to go over the Coulomb potential, but it could just tunnel through the barrier. Without tunneling, we cannot see the stars that we see in the night sky as they are not ignited. Tunneling is also used in the scanning electron microscope, which gives us a magnification of really high power. It is also being used in ammonia inversion. So guys, tunneling is seen in most of the situations in the world. Hope you guys enjoyed the video. Have a nice day.